Today we're going to continue with the vectors topic, and we're going to be covering representing motion using vectors. So, as mentioned previously, vectors can be used to represent a whole variety of situations, and a very common one is the motion of objects as they're traveling in linear directions. So, an easier way to represent vectors when we're using motion is to use polar form. And so essentially the polar form of a vector is where we represent it using a radius and a magnitude. Sorry, a radius and an angle. So the radius, which is the magnitude, extends from the origin. So we use a radius of r and we have an angle of theta. And we can use those two things, the r and the theta, to represent any vector we want from a position vector standpoint, because this theta can go all the way around and this r can go out as long as we want it to. But if we want to be using the radius and the theta from the polar form, and we want to use that in our xy coordinate system, we have to use these conversions where this is our x and this is our y. So this is just another way to represent vectors. And we can represent any vector we want like this. So let's look at some examples as to how we might use that in motion. So a body experiences an acceleration of -10 meters per second in a direction of 135 degrees. Find the vector for the acceleration of the body. So here we've been given it in terms of an acceleration, or a magnitude in this case, and a direction in terms of an angle. So it's going to be best for us to represent it using that previous format where we had our r cos theta and our r sine theta. So in this case, a, or our acceleration vector, is going to be equal to -10 cos 135 degrees, comma, -10 sine 135 degrees. And that's just from the previous slide, using the same format. So importantly, this 135 degrees is the second quadrant angle for 45. So that means that it's going to be the magnitude of the 45-degree angle, but for cos it's going to be negative, and for sine it's going to be positive. So what we get here is that this becomes -10 minus 1/√2, comma, -10 times positive 1/√2. And so then this becomes, in brackets, 10√2 all over 2 if we're simplifying the denominator, or rather rationalizing the denominator. And this becomes -10√2 all over 2. And final step, we simplify this fully by removing the 2's, and we get that a is equal to, brackets, 5√2, comma, -5√2. So in this case, we were given a magnitude and an angle at which the vector was positioned, and we just had to basically substitute it into that format. But importantly, we use this to find the acceleration of a body. So you might be given a question like this, be asked to find the acceleration, and then be asked to do other processes involving that acceleration. Maybe you have to combine multiple accelerations or something along those lines. So this is just to get you familiar with the fact that we can absolutely use vectors to represent any motion we want, and realistically nothing changes too much. It's just the same vector processes that we're used to. So moving on to a slightly harder example, we have a plane's controls are set to a speed of 250 kilometers per hour on a bearing of 40 degrees, but there is an easterly wind of 55 kilometers per hour, wind from the west. Find the actual speed and bearing of the plane taking into account wind. All right. So if we want to take into account the wind, then we end up with this situation. Let's draw this out. So let's say we have our plane, and it's not necessarily moving north or south, it's just moving in any old direction we want it to. But then we have a westerly wind, so it's a wind coming from the west, which means we're going to then have another vector forcing our plane to move this way, So our resultant vector is going to be here, which, as you can see, the magnitude is slightly larger than the normal vector, which means and considering that the magnitude of these vectors represents the speed, we do expect the speed of our plane to increase because of this westerly wind, despite the controls only being set to 250 kilometers per hour. So that basically just means that the plane is pushing itself up to 250 kilometers per hour, but then there's an external force pushing it to go even beyond that. And it'll also, as you can see, deflect the direction. So these are all important things to take into account when flying planes or when working these sorts of things out. And pilots use these sorts of wind changes to chart their courses when they're in a plane. And they have all sorts of instrumentation to help them do that. So let's call the plane's vector u and the wind's vector v. And so in this case, we can represent our u vector using the same format we used earlier. So we have our u vector. And in this case, note that this 40 degrees is measured from the north because this is a true bearing. So that means that this angle here is 40 degrees. But whenever we do our angle in polar coordinates, the angle isn't actually measured from the north, it's measured from the positive x-axis up. So it's going to be pointing in the positive x-axis. So this is the angle, sorry, beyond that. This is the angle that we really want. So we don't want 40, we're going to want 90 degrees minus 40 because that's going to give us the remaining amount. So we actually want 50 degrees. So our resultant our resultant velocity vector for the plane is going to be given by 250, and this is kilometers per hour because that's our magnitude. But then our angle is going to be 50 degrees, not 40 degrees. So it's going to be then also 250 sine 50. And for our wind, we're given a magnitude of 55 kilometers per hour, and it's pointing in the westerly direction. So that means that the angle is 0 with the positive x-axis because the v and the x-axis will be parallel. So we get 55 then cos 0 degrees, comma 55 sine 0 degrees. And from here, once we represent our u and our v vectors, we can then add them, which is what we want to be able to find the resultant black line vector here. And so what we do now is we just add the two. So we add them, and this gives our new vector, which is the resulting vector that we had from earlier. So this is we add the x components and the y components separately. So this becomes 250 degrees plus 55 because cos 0 is 1. And then that's also going to be 250 sine 50 because sine 0 is 0. So we don't have to take into account the v component. All right. So now we're in a really good position to be able to find the magnitude and the direction. So let's start by finding the magnitude. So for the magnitude, you have the formula for it. We just do what we always do. So we want the magnitude of u plus v. So this is going to be 250 cos 50 degrees plus 55 all squared plus 250 sine 50, I'm running out of room here, squared. And if you put that into your calculator, trust me, it's going to be approximately 288 kilometers per hour. So the plane is actually moving in a speed of about 288 kilometers per hour. So as we suspected, it's more than what was originally set by the instruments. But now the bearing. The bearing's a little bit tricky because there's a slight trick that you might miss out on, particularly if you didn't notice that we had to use 50 degrees here, not the 40 degrees. But for bearing, we have another way of finding our angle, and that is tan theta is equal to y over x. And so this becomes, we take our y and our x components, so this becomes 250 sine 50 degrees all over 250 cos 50 plus 55. lot of 5s in there. And if we rearrange this, if we move the tan over and we solve all of this and put this into a calculator, we should get approximately a theta is equal to 42. Now, that isn't the angle we want. That's not going to give us our bearing. Well, it's going to give us our bearing, but it's not our bearing, because that's the angle from the positive x-axis up to our vector. What we want is our bearing. So now we do want the line from north going around. So we have to do what we did earlier, except now with this 42 degrees. So we have our bearing. So our bearing is 90 degrees minus 42 degrees, or it's actually 48 degrees. And that's using true bearings, like what they used up here. So what did we learn during this lesson? Well, you learned that when we're trying to understand motion in terms of vectors, we often like to use polar coordinates, which defines any vector for a given position vector in terms of an angle and a radius. And so that really helps to represent motions using vectors, and that representing motions using vectors is usable at all. So we can apply vectors to many motion problems and really get some interesting results and be able to figure out a bit more about the situation. Anyway, I hope that was helpful, and I hope to see you guys next time.